In this lecture video, we're going to introduce the idea of the imaginary unit and complex numbers. Up until this point, we have not allowed negatives to be inside of our square roots. However, there's another set of numbers called the complex numbers that do include such roots. The imaginary unit I is defined to be the square root of -1. That means that I squared is equal to -1. Complex numbers are numbers of the form a plus bi, where a and b are real numbers and I is the square root of -1. The real number a is called the real part, and the real number b is called the imaginary part. If b is not equal to 0, that is, it has a multiple of the imaginary unit I, then the complex number is called an imaginary number. If b is equal to 0, then the complex number is a real number. An imaginary number of the form bi, that is, a is equal to 0, is called a pure imaginary number. Let's try out some examples. First, we are simply going to express these radicals in terms of I. Notice that each of them have a negative inside a square root. Using the product property, we can rewrite the square root of -100 as the square root of -1 times the square root of 100. The square root of -1 is I, and the square root of 100 is 10. And the proper way to write this would be 10i. Looking at the square root of -72, we can again write this as the product of the square root of -1 and the square root of 72. The square root of -1 is I, and since 72 is divisible by the perfect square 9, I'll rewrite it as the square root of 9 times 8. Since the square root of 9 is 3, we have I times 3 times the square root of 8. And the proper way to write this is 3i root 8. While we typically want to write the I last, in the case of a square root, putting the I on the end could be confusing because we might accidentally think that the I is inside the square root. Now let's look at the negative square root of -54. Beginning again with the product property, we have negative square root of -1 times the square root of 54. The square root of -1 is I, so far we have -I, and the square root of 54 we could rewrite as the square root of 9 times 6. The square root of 9 is 3, so this simplifies to be -3i root 6. To add complex numbers, we simply add the two real parts and add the two imaginary parts. So in example 2, we begin with 9 minus 2i plus 17 plus 6i. We will simply add the real parts, 9 and 17, and we will add the imaginary parts, -2i and 6i. This gives us 26 plus 4i. Looking at the next example, we have 3 plus 8i minus 12 minus 7i. Subtraction works like the opposite of addition, like we're adding a negative. We could even rewrite this as 3 plus 8i plus -12 plus 7i. And adding these two complex numbers together, we have 3 plus -12 plus 8i plus 7i. This simplifies as -9 plus 15i. Finally, let's add 3 plus 12i plus -8 plus 15i. Adding the real parts together, we'll have 3 plus -8. And adding the imaginary parts together, we'll have 12i plus 15i. This simplifies to -5 plus 27i. Notice that in all three cases, I wrote the answer in the form a plus bi. Now let's try multiplying complex numbers. In example 3, we need to multiply 8i times 15i. Consider multiplying 8x and 15x. We would simply multiply 8 and 15 and get 120, and x times x we write as x squared. The same is true for 8i and 15i. We just need to be careful of how we simplify. We start with 120i squared. But recall that I squared is equal to -1. So this is 120 times -1, or -120. Now let's multiply the square root of negative 21 and the square root of negative 28. We begin by first writing both of these radicals in terms of I. The square root of negative 21 is I root 21, and the square root of negative 28 is I root 28. We can also simplify the square root of 28. 28 is divisible by the perfect square 4, and since the square root of 4 is 2, we end up having the product of I root 21 and 2I root 7. Now when we multiply, we have I times 2I, or 2I squared, outside of the radical. And multiplying our two radicals together, we have the square root of 21 times 7, or the square root of 147. I squared is equal to negative 1, so this is just negative 2. And consider that 147 came from the product of 21 and 7. Since 21 is equal to 3 times 7, 147 is equal to 3 times 7 times 7. So we know that the square root of 147 is equal to 7 squared times 3. And since the square root of 7 squared is 7, we end up with negative 14 root 3. Please pay careful attention to the fact that we first wrote these two radicals in terms of I. If we multiplied them together first and had the square root of negative 21 times negative 28, we would have the square root of positive 588, which would simplify to positive 14 root 3, which is not the same answer. So make sure you always switch to using I notation first before you multiply. In example 4, we are still multiplying. We begin with 4I times 7 minus 3I. We will distribute just like we did when these were x's. We have 4I times 7, or 28I, and 4I times negative 3I, which is negative 12I squared. Simplifying, I squared is equal to negative 1. So this is negative 12 times negative 1, or 28I plus 12. Writing this properly, we have 12 plus 28I. Now let's look at 6 minus 5I times 10 plus 3I. Distributing, we first have 6 times 10, or 60, then 6 times positive 3I, or positive 18I, then negative 5I times 10, or negative 50I, and finally, negative 5I times positive 3I, or negative 15I squared. Simplifying, we have 60 plus 18I minus 50I, or 60 minus 32I. I squared is equal to negative 1, so we have negative 15 times negative 1, or positive 15. And 60 plus 15 is 75, so we end up with 75 minus 32I. Now let's multiply 8 minus 7I and 8 plus 7I. We will again distribute. We have 8 times 8, or 64, 8 times 7I, or positive 56I, negative 7I times 8, or negative 56I, and negative 7I times positive 7I, or negative 49I squared. Simplifying, we have a positive and a negative 56I. With those simplifying to 0, we have 64 minus 49I squared. I squared is negative 1, so we have 64 minus 49 times negative 1, or 64 plus 49. Adding, we have 113. Notice that we multiplied two conjugates together. We have 8 minus 7I times 8 plus 7I. And the result is 64 plus 49, or 8 squared plus 7 squared. And this is always true when multiplying complex conjugates. In general, the product of a plus bi and a minus bi is a squared plus b squared. Be careful not to confuse this with our earlier properties that a plus b times a minus b is equal to a squared minus b squared. Having the I involved changes it to a squared plus b squared. Let's now multiply 11 minus 4i and 11 plus 4i. Since these are complex conjugates, this is going to be 11 squared plus 4 squared, or 121 plus 16, or 137. Now let's talk about dividing by a complex number. We know that it's improper to leave a root in the denominator, and we've learned ways to rationalize the denominator. Since I is equal to the square root of -1, it's improper to leave I in the denominator as well. It's equivalent to leaving a square root in the denominator. So when we divide by a complex number, such as 15 divided by 8 plus 6i, we'll use our conjugates to rewrite the expression without I in the denominator. We know that 8 plus 6i times 8 minus 6i is simply equal to 8 squared plus 6 squared, which is a number without an I. So let's multiply the numerator and the denominator of this fraction by 8 minus 6i. In the numerator, this gives us 15 times 8 minus 6i. And in the denominator, we have 8 squared plus 6 squared. Simplifying, we have 15 times 8, or 120, and 15 times -6i, or -90i. In the denominator, we have 64 plus 36, which simplifies to 100. Now we no longer have an I in the denominator, but we do need to simplify some more. Notice that 120 and 100 have common factors, and so do 90 and 100. Consider this fraction broken up into the difference of two fractions, 120 over 100 minus 90 over 100i. 120 and 100 are both divisible by 20, so this simplifies to 6 over 5. 90 and 100 are both divisible by 10, so this simplifies to 9/10 I. So our final answer is 6 over 5 minus 9 over 10 I. Let's try the same process again with this quotient. We have 1 plus 5i divided by 3 minus 4i. We will once again begin by multiplying the numerator and the denominator by the complex conjugate of the denominator. This gives us 1 plus 5i times 3 plus 4i in the numerator and 3 squared plus 4 squared in the denominator. Distributing in the numerator, we have 1 times 3, or 3, 1 times 4i, or 4i, 5i times 3, or 15i, and 5i times 4i, or positive 20i squared. And in the denominator, we have 9 plus 16. Since I squared is equal to -1, positive 20i squared is equivalent to -20. So combining like terms in the numerator, we have 3 minus 20, or -17, plus 4i plus 15i, or positive 19i. Adding in the denominator, we have 25. To write this in proper complex number notation, we would separate this into two fractions. Our A, 19 over 25, and our B is positive 19 over 25. So we have -17 over 25 plus 19 over 25i. Let's look at one last example. In example 8, our denominator only has one term, 5i. When we simply have a term with an I in the denominator, we'll multiply the numerator and the denominator by I to rewrite the fraction without I in the denominator. With 8 plus 3i divided by 5i, multiplying by I over I gives us 8 plus 3i times I in the numerator and 5i squared in the denominator. Distributing in the numerator, we have 8i plus 3i squared. And since I squared is -1, we have 8i minus 3 divided by -5, or -3 plus 8i divided by -5. Simplifying, we have -3 over -5 minus 8 over 5i. And with these two negatives canceling out, we have positive 3/5 minus 8/5 I. That concludes this lecture video on the complex numbers.